Hello everyone. My name is Hoffmann. I'm a PhD student at the Hoffmann Center in Geesthacht. That's close to Hamburg. And today I think I will talk about a process which probably most of you don't really know. It's called friction surfacing. And I'm really curious if someone of you knows the process. You might raise your hand if you know it. Oh, one person or two. So most of you will probably learn something, at least a new process today. And in this study we wanted to show if the friction surfacing process is a suitable process for additive manufacturing. Before I start with the contents of my presentation, I will give a short motivation why we investigate this friction surfacing process. It's basically intended for, or it was used for tool repair or crack repair. And in our project, we are interested in finding applications for the aerospace industry. For example, single layer applications like local reinforcements, for example, for stringers or for skin parts, which usually are done by riveted plates. With our process, we could simply make a single layer deposit to do that. Another idea is to use it as crack stoppers. Here I brought a picture. It's indicated here in those red boxes around a window frame. And the last point is to develop a multi-layer application, which then is the link to the additive manufacturing. That's why I'm here today. And here's the idea to have some applications in additive subtractive manufacturing, because in the aerospace industry, large parts are machined out of big blocks, and with this additive subtractive technology, a lot of waste can be reduced. So advantages of the friction surfacing process compared to the additive manufacturing processes we all know from the presentations is that, especially compared to the powder-based processes, it's easier to handle because we don't have the powder, and also it's safer. Another advantage is that we don't have local melting in our processes, which requires less energy, and it's also has lower environmental requirements to our process. For example, when we're joining aluminum alloys, we don't need shielding gases. As I already said, we don't have melting in our process, which also leads to the fact that we don't have typical defects in our welds afterwards, such as porosity or hot cracking, as we have seen here a lot of times today. And what's also very important is that we have a high range of material combinations which we can join. This also means that we can join dissimilar material combinations. For example, we can join aluminum alloys to steels or to titanium alloys, but we can also join steel and titanium alloys, for example. First of all, I want to introduce you all to the process itself, the friction surfacing process. Afterwards, I want to show you the setups we use in our labs, and afterwards I will come to the results of this case study here. So the friction surfacing itself can be divided into 4 steps. It only requires 2 materials. One is the substrate material, which can also be the part which is deposited in the end, and the consumable stud material, like shown here. And the first process step is to position it to the starting point. Afterwards, we start the rotation of the stud with a certain rotational speed, which is one of the main process parameters. And afterwards, when the final rotation speed is achieved, it's pressed to the substrate plate. Therefore, we have 2 different control types. One control type is a force control or load control type, which means that we control the load with which the stud is pressed to the substrate. Another mode is the position control, where we control the position of the stud in the actual direction. So due to this contact with the high rotation and the actual load, we achieve friction between the two interfaces, which results in a heat generation, which then leads to a plastical deformation of the tip of our stud. And afterwards, this plasticized stud material will then create a bonding with the substrate material due to diffusion processes, but also due to mechanical interlocking, due to surface roughness of our substrate plate. Also in this part, the heat generation due to the friction shifts to heat generation due to plastical deformation, which is very useful when we want to deposit layers, like we do in the third step of our process. When we superimpose a translational movement with a certain speed, we are able to build a length deposit. Another fact that I want to mention is that we don't simply have to do those straight lines. We can also go basically every desired geometry. And disadvantages of this process is that we have a generation of a flash material, which is indicated in here, which is material out of the outer part of our stud, which is not deposited to the substrate, which decreases our deposition efficiency at the moment. But there are already some concepts how to avoid or how to deposit this flash material during the process to increase the productivity of the process. Unfortunately, I haven't brought any videos today, but here I brought some pictures how it's looking at our machine. Here you can see that there has already been a first deposit onto the substrate material, and in this process we're doing a second layer, like we will do when we go for additive manufacturing. And for the second layer, all that I've mentioned before for the first layer is all the same. Okay, now we come to the setup in our labs. On the right hand side you can see the machine we're using. It's a pretty big machine, I would say, and it's custom designed for our processes, especially for the friction surfacing process. We can also use it for other processes, but it's mainly used for the friction surfacing process. And the main components are the working table, where we can fix our substrates or our parts, and the spindle up here to fix our studs. We can fix studs up to a length of 500 millimeters with a diameter of 30 millimeters. In this study, we used for both the substrate and the stud material the aluminum alloy 2024, and the diameter of the stud in this study, and like in almost every study we're doing at the moment, is 20 millimeters, and it has a length of 125 millimeters. Our machine is capable of applying loads up to 60 kilonewtons, rotational speeds up to 6,000 revolutions per minute. We can move the table with speeds up to 20 millimeters per second. And overall we have a maximum torque about 200 Newton meter, which can be achieved during the processes. The working space or the working table we have has the dimensions 0.5 to 1.5 meters. Okay, now I will come to the study which we did here for the additive manufacturing. So what we did here is that we deposited multiple layers onto each other, and such a stack can look like this. Here on the right side, the top view and the side view. And the selected parameters in these studies were the same for all the layers, which means that we applied an extra load of 12 kilonewtons, rotational speed of 900 revolutions per minute, and a deposition speed of 8 millimeters per second. So these parameters were selected based on another study for a dissimilar material combination for a deposition of the 2024 to 7050. But we also showed that it's working also for the similar material combination. So what we did is we deposited 40 layers. With one stud, we were able to do 3 layers. In total, we have a height of this multi-layer structure of about 50 millimeters, which results in a layer thickness of 1.25 millimeters per layer. The total length of the structure we did was 125 millimeters. Here you can clearly see that this is another structure which I have a photo here of. And yeah, all those parameters lead to a deposition rate of 150 cubic millimeters per second. I also wrote here that we have a bonded width of 15 millimeters. There I have to say that the total width of our layers is in most cases close to the diameter of our studs. In this case it would be 20 millimeters. But as you've already seen in the slide before, that the outer part of the stud material goes to the flesh, we don't have good bonding at the edge regions. That's why we're always talking about the bonded width, which is in this case 15 millimeters. So those unbonded regions at the edges were then machined off in the next step, and afterwards, we were interested in extracting our samples. This can look like this sketch here on the left-hand side. This is the machined area. From this area we could have extracted tensile specimen. And here, this is what we did in this study. We looked at the microstructure and at the hardness of our sample. So on the right-hand side, you see how this will look after machining the small part. And we were interested in the microstructure in different planes in our structure, and also in the hardness in those structures. So those planes are oriented in all three axes. And also three planes are located in the upper part of our structures, and two planes are located in the interface region between the substrate and the studs. So what we did is, first we had a look at our stud base material, and we can clearly see that we have cranes oriented mainly along the 001 and 111 direction, and have a mean crane size of 4.47 micrometer, but we have a very high standard deviation due to those very small particles in here. When we then apply our process, due to those high plastic deformations, we see that we have a very nice grain refinement, and that we also have no longer this preferred orientation as we have seen here, but we have more random orientation all over our planes. But what we can also see is that we have slightly smaller cranes in our interface regions compared to the planes in the upper part of our stacks. So here on this slide, I will more focus on the crane sizes. I think it's more easier to see this here in this graph than in the IPF maps. And we can see that compared to our base material, we have a crane refinement of approximately 50%. And that's why we're expecting in our whole structure a very low anisotropy regarding the crane size. In the same regions we also did afterwards, after the EBSD, we did hardness measurements, and here we again see that we have a very homogeneous hardness distribution in our stack. But what we also have to mention is that the hardness decreased compared to our base material, from which was close to 160, then decreases down to approximately 110. And this means that we have a decrease of about 35%. We expect that in our base material, which was a T351 temper condition, afterwards, not after our process, that changes in the size and in the composition of the precipitates might lead to those changes. To come to an end, I want to shortly summarize what we did in this basic study about the multilayer approach. We see that after our process we have a significant decrease of the texture in our structure, and slightly, significantly, we find grains of about 50%. Homogeneous grain sizes and hardness distributions were observed after the process in our multi-layer stacks, but we have to say that we had a decrease of the hardness, so now we only have about 75% of the base material hardness. This then leads to the further steps, which seems to do a process parameter optimization to increase our mechanical properties of our stacks to reach hardness values, for example, close to that of the base material. And also afterwards, after we have done this optimization, we are interested in also showing or looking at the mechanical properties in tensile tests, for example, in different orientations, to see if we can also expect this isotropic behavior that we have seen in the grain sizes and in the hardness. Also, it's possible to increase the mechanical properties by suitable heat treatment. And what's also very important is the last point here on this slide, which says that our goal is also to develop the process further into a continuous process, because at the moment the process itself is very discontinuous, which means that after each layer the process has to start from new. And also if the stud is completely consumed, we have to change the stud to start a new process. So therefore it makes sense to have a continuous process which can then be used as an economically feasible additive manufacturing process. So I want to thank you very much for your attention, and now I'm open to your questions. If you have some now, or if you have them later, you can also come to me during the lunch break. Thank you very much.